Hi, my name is Dan Zhao. My project is called First and Last Mile, which is a popular origin and destination detection platform. So I guess the first question would be, what is first and last mile? The first mile problem has been used to describe the difficulty of getting people from starting point to transportation hubs. Similarly, last mile problem is about getting people from transportation hubs to destinations. For people who use public transportation, when they get off the subway or bus, how can they get to their final destination if it's too far for walking? It could be taxi or by bike. So if we can know the most popular destination from our two each transportation hubs at different times of the day by analyzing the taxi or bike sharing data, it will help public transit agencies to plan their bus routes accordingly. Sharing by company and scooter companies can better allocate resources, especially during rush hours. So here is my demo. The user can choose origin or destination, the year, the month, the vehicle, the subway station, and the max searching distance. And then once the user clicks the submit button, the platform will immediately show the map with top destinations of trips within the max searching distance from the subway station. Each point here represents a popular destination, and the size and color indicates the popularity. The platform will also provide a table with detailed information of the destinations, such as distance, cost, duration, and passengers, and etc. Here is my data pipeline. I use data sets of green and yellow taxi and city bike in New York. The data sets are over 300 gigabytes. The raw data are stored in S3 as CSV files. Geocoding work is done by Python. The data are pre-processed by Spark and stored back to S3 in Parquet format to save some space. And then I use Spark to ingest and process the data. The aggregated results are stored into PostgreSQL with PostGIS extension, which has some convenient geo functions. Finally, Dash is used to build an information querying UI. The first challenge I got in this project is inconsistent schema because the trip files are uploaded monthly with different schema. As you can see from the example of headlines from trip files, some files have location ID as location information, while others have longitude and latitude as location information. The solution here is to define a general schema when ingesting and then broadcast join the data with location ID lookup table. And then needed columns are selected and stored back to S3 in Parquet format to save some space. The second challenge here is reverse geocoding. As I mentioned before, in some trip files, taxi location information is stored as location ID in shapefiles, and also there is no longitude and latitude of subway stations. The solution here is to generate two lookup tables and join them with the datasets. The first one is to generate location ID lookup table by reverse geocoding the neighborhood polygons from shapefiles with Python. The second one is to generate subway station lookup table by averaging the longitude and latitude of entrances. The third challenge is aggregating points. Why need to do that? Because points with slightly different longitude and latitude can actually belong to the same destination. And if I don't do that, there will be too many destinations for UI to show on the map. And even it can be shown on the map, it will look really messy. And also I want to achieve lower latency. So I came up with 4 possible solutions. The first one is to run the longitude and latitude, which is simple and lead to irregular shapes. The second one is to use taxi location ID, which will cause the blocks to be too big. The third one is to use k-means algorithm to aggregate locations to, for example, 100 blocks. It is a nice one, but will cause high latency. So finally, I use geohash in my project. By geohash, the longitude and latitude of a point are hash coded to a string which represents a rectangular containing the point. It is quite important to choose proper precision when use geohash. Because the higher precision I chose, the smaller area it represents, and thus there will be more records to store in the database, which will further lead to higher latency. Here is an example when the precision equals to 6 or 7. As we can see here, when precision equals to 7, the area of the rectangular is similar to a block in the real world. So I choose precision as 7 in this project. That's all for my project. Here is something about me. Again, my name is Dan Zhao. I just earned my master's degree at University of California, Berkeley. My analytical work in my research made me realize the importance of reliable data pipelines. So I am now passionate about designing reliable and efficient data pipelines and also prepare data for our data teams to use in the company. That's all. Thank you for listening. Please feel free to refer to my slides and GitHub for more information. And if you have any questions, please feel free to email me. Thank you.